Hello, thank you very much for having me today. My name is Oliver, and I'm currently doing my master's in Dr. Hagelin's lab. I'd like to present to you synergistic effect of senolytic combination reduces intervertebral disc degeneration. Low back pain is a global health problem experienced by 80% of the world's population. It is directly related to intervertebral disc degeneration, and this degeneration has been linked with an accumulation of senescent cells. Cellular senescence is irreversible and characterized as non-proliferative, however metabolically active. Yet, this protective mechanism has its caveats. These cells release nasty pro-inflammatory cytokines and chemokines, coined senescent-associated secretory phenotypes, or SASP for short. These SASP factors affect the tissue milieu and progress degeneration and pain for patients with low back pain. Senolytic treatments are a class of compounds that selectively induce death of senescent cells and improve health in humans. Our lab has shown that orthovanillin, a natural senolytic derived from curcumin with antioxidant and anti-inflammatory properties, and RG7112, a synthetic FDA-approved senolytic, both selectively target and remove senescent cells. Our lab has never combined the two senolytics together, but the truth of the matter is that senescent cells are heterogeneous, and a combination of senolytic agents are often needed to target multiple senescent-associated pathways. We decided to increase senescence in our cell population to see how effective the senolytic treatment was. There are models used to induce senescence, such as radiation and peroxides. As these methods are effective, we believe they do not represent the physiological method at which cells in our bodies become senescent. We recently published that toll-like 2,6 receptor agonist, PAM2, increases senescence. It does this by increasing pro-inflammatory cytokines and in a paracrine fashion induces senescence as it's believed to occur in the human body after trauma and stresses. As we can see, PAM-treated cells secrete about 2 times higher levels of cytokine IL-6. Also, PAM-treated cells express roughly 5% higher levels of P16, which is a senescent marker compared to the vehicle. Our lab is very fortunate to have a collaboration with Transplant Québec. We receive surgical samples from patients undergoing disectomies and culture the intervertebral disc cells. We either make monolayers and incubate them with PAM for 42 hours, then 6 hours with senolytics, or make pellets of cells which take 2 days to form, then treat with PAM for 2 days, and then 4 days with senolytics. Afterwards, we incubate them in regular media and every 4 days collect and replace the media for a total of 4 times. We previously showed that 5 micromolars of RG and 100 micromolars of ovanillin had the best senolytic effect. We decided to make serial dilutions of each of the drug and select the best concentration to then combine. These are the Monolayer experiments. Our control in green was PAM treated, and our negative control in orange was vehicle. As you can see, 5 and 2.5 micromolars in blue and 150 micromolars of ovanillin in red had the best effect, whereas anything below those concentrations had little or no effect compared to the controls. These experiments also confirmed that 5 micromolars of RG and 100 micromolars of ovanillin were equally effective, as they did not have significance compared to each other. Next, we selected 5 and 2.5 micromolars of RG and 150 micromolars of ovanillin as the best concentrations and combined them. All the combinations had greatly reduced senescence using P16 marker compared to the control, but this was the first real evidence that combining the two senolytics had a greater effect than the drugs alone. As we can see, the combination 5 plus 100 in purple had significantly reduced senescence compared to both 100 micromolars of ovanillin and 5 micromolars of RG in red and blue, respectively. This represents a 26% reduction from 5 micromolars of RG and 34% reduction for 100 micromolars of vanillin from the combination. We wanted to see if there was an increase in apoptosis. As you can see, the PAM-treated cells in green had an increase in apoptosis compared to the negative control in orange. This can be explained by the pro-inflammatory response PAM2 creates targeting TLR26 receptors. Part of that inflammatory response can be the secretion of TNF2 alpha, which can cause further a pro-inflammatory response or apoptosis in neighboring cells. But the difference between the control and the treatment is the effect of the senolytic drug. Again, the 100% ovanillin and 5 micromolars Rg is significantly more effective at removing senescent cells than the drugs alone by about 30%. We ran preliminary ELISAs of IL-6 and IL-8 pro-inflammatory cytokines of the media swabs from our pellet model experiments. We decided to use 2 models for the pellets, one treated with PAM and the other without. Afterwards, they would all be treated with senolytics. The combination treatment without PAM for both IL-6 and IL-8 showed a significant decrease compared to the control, and most importantly to the senolytics alone, further supporting that the combination has a greater effect. IL-6 with PAM to the right demonstrated similar trends, but was not significant as more samples was needed. We ensured that there was no cytotoxic and negative effect of the serial and combination treatment of the cells. Here, we see that the cell viability from our pellet experiment supported by Alamar Blue is similar or more active to that of the control. It is also supported by live dead viability and cytotoxicity 2-color assay. It was interesting because for some samples, the control was less fluorescent than the treatment groups, but for others, control and treated groups had the same fluorescent intensity. The P16 supports that the combination of Rg and ovanillin has a greater effect than Rg or ovanillin alone. The combination has a greater effect at reversing and further improving the influence of PAM2 by selectively removing senescent cells via apoptosis, confirmed by the increased levels of caspase-3. The combination improves the tissue milieu by reducing the production of SAS factors better than the senolytics alone. The probable explanation of the synergistic or additive effect is that ovanillin and RG7112 is a target of different and overlapping senescent pathways, therefore increasing its ability to remove more of the heterogeneous senescent cell population. Next, we will evaluate the pellet model using similar markers and potentially run ex vivo experiments. We hope this knowledge can further help our understanding in tissue degeneration, senescence, and help improve or even reverse intervertebral disc degeneration for patients with low back pain. I'm very fortunate to be part of such a great and supportive lab. I'd like to thank my PI, Dr. Hagland, and our whole team. Thank you very much. Thank you very much for listening.
Wow, Oliver, this is a really awesome presentation. Thank you so much. I think I learned quite a bit. So now we're going to move on to the question. So if anyone has any questions, please feel free to chime in. If not, I'll actually, oh, sorry.
So Oliver, a very nice presentation. So is this for early disc degeneration? How would you use it clinically? Is it for early or just what stage?
Well, right now we're actually looking at different models, such as the mouse models. So right now we're looking if it's going to be a preventative treatment or if it can be a treatment that can reverse degeneration. So right now we're actually evaluating the combination within the mouse model, but we know that oral supplements of the treatment might not necessarily be as effective because the intervertebral discs are not a tissue that interacts with the bloodstream. And so it might actually need to be treated directly with injections. But again, it's to be evaluated.
Okay. So the cells that you are using are from human. Where are those from? Are these NP cells or AF cells or just a soup?
So what we do is that we receive surgical samples from patients undergoing disectomies. So we know that this tissue is actually degenerative because these patients have extreme low back pain. So right now they're at the end stage of treatment, and that is the radical treatment of actually getting their discs removed. And so what we do is that we receive these surgical samples, and then afterwards we take the NP and AF, separate them. We proliferate them, and afterwards we make cultures of 50-50 NP and AF, and afterwards we run our experiments.
Okay, thank you.
Thank you.
Oliver, maybe this is a very general question, but maybe you can expand a bit on senescence versus apoptosis and cell death and Whether or
Yes,
not you get both, or is it strictly senescence?
well, the problem with apoptosis and senescence is that they're slightly, if you look downstream of the pathways, they're very correlated together. And so cells will either go from one or the other. So if you actually like, give cells a TNF alpha, one pathway might be NB, NFB kappa, that stream. And so from there, it's going to create a more pro-inflammatory pathway. As for the other pathway of TNF alpha is actually apoptosis. And so senescence is a protective mechanism against cancer and things like that. So either the cell will go from one way or the other. And so part of our stains actually support both. So we've actually done stains with Ki67, which is a proliferative marker, and it does seem to increase, and as well as the other side, which caspase-3, it increases as well. So that's why we've shown that these senolytic drugs are actually helping at selectively removing the senescent cells while allowing the healthier tissue to actually proliferate and grow.
It's a good explanation. So I was a bit distracted. Apparently, students at the MGH don't have any internet, so I think that's why there's less people here than there should be.
That's too bad.
Yeah, it's good. Thanks for that answer.
Thank you, Dr. Bella.
If anyone has any other questions,
I would like to ask the question in what was the reason in choosing Alamar Blue or a Presto Blue type of assay, and would have been a different outcome if you would use something based on tetrazolide like an MTT, XTT, or any other type of those assays? Why that one and not the other one? I'm just curious.
Yes, of course. So Alamar Blue is actually available at our lab. So obviously it was a trivial selection to see viability, but that isn't really, we're not really looking at that for now. Right now, we're looking at the senescent markers, which are the really important markers. But it was just kind of to see that it's not killing anything. But obviously further down the line, if we really want to make sure that the treatments are not killing anything or anything like that, then we would definitely go for another marker to add to the Alamar Blue.
Thank you.
Thank you.
Okay. Thank you, Oliver. So now I'd like to introduce our guest speaker. Our guest speaker is Professor Ramos. So Professor Ramos has a BSc in chemistry, a PhD in physical chemistry from the University of Sao Paulo. For those of you who don't know, they're Brazilian universities. That's the best university in Brazil. She was fortunate to be a visiting student, PhD student in the best city on the planet, which is Bristol. And now she's an assistant professor and heads up the Surfaces and Colloids Laboratory at University of Sao Paulo. So her group studies on biomineralization using Langmuir monolayers and Langmuir budget films. And she has the overall kind of aim to promote and accelerate bone regeneration. She holds a patent on deposition of coatings using phospholipids. And she was awarded the best PhD student in the chemistry category in Brazil nationally in 2021. And she studies also the use of strontium and how strontium affects biomineralization, which is the topic of her talk today. Welcome, Professor Ramos.
Thank you, Professor Bartlett, for your kind introduction. I will share my screen. Can you see my screen? Let me just move you to the other side. Okay, so I'm very glad to be here today talking to you a little bit about the work that we have developed in the physical chemistry of colloid and surface laboratory. I know that maybe the chemist or the chemistry here is not very close to your field, so I will try not bore you too much with too much chemistry, but much more with the application of the materials and the strontium-based materials that we have prepared here. So first, I'd like to introduce my country to you. So here we have Brazil, here São Paulo state. As Professor Barlet said, São Paulo state is the richest state in Brazil. The University of São Paulo is the best university in Brazil and is maybe the first also in Latin America. We have 5 campuses spread through the state. My campus is located here in Ribeirão Preto, and São Paulo city is like 300 kilometers away from Ribeirão, but trust me, for the Brazilian distance, it's very close to us. I'm showing you a little bit about my city. So Ribeirão Preto, we have a very beautiful historical center, cathedrals. Here it's the entrance of the university. Our university used to be a farm in the past. So we have these colonial buildings, lots of trees. It's still like a farm. We have the lake, the main build of the former farm. And in my opinion, one of the most beautiful places I've been, the view from the lake in my city. So if you want to know a bit more about the University of São Paulo and Ribeirão Preto campuses, I left here this video for you to watch. We have here also a medical school, a dentistry school, law, physics, chemistry, biology, psychology, education, nursing, physical education, among others. So it's very nice to me to work here. Since I'm a materials chemistry, I can prepare materials for my colleagues especially from medical and the dentistry school to apply them. So it's the collaborative work goes well in this way. And now I'll talk a bit about the studies that we have developed here in the laboratory that I coordinate. So the first topic of my talk will be the challenge of treating osteoporosis. And so I will talk to you about 4 types of strontium-based materials that we have developed here. The first, some flavonoids-based complex containing strontium, some nanoparticles containing strontium, some bond cements, and some coatings that we have deposited on titanium, aiming for applications in implants. So first, as you know, the osteoporosis can be caused by an unbalance between the activity of osteoblasts, the cells responsible for the mineralized bone formation, and osteoclasts, the cells responsible for the bone resorption. Although bone seems to be an static tissue, actually it's under renovation during our lives, and an unbalance in which the osteoclasts have more activity than the osteoblasts will cause loss of bone density related to osteoporosis. In the past, there was a drug used to treat osteoporosis based on strontium. However, due to some cardiac and some vascular, or in general, some pathological mineralization caused by this drug, it was forbidden in all, I think, in all the countries where they were used. So here we propose a new therapy also based on strontium, but trying to keep the safety of this ion for the osteoporosis treatment, or more in general for treating mineralization problems. So why strontium? First, strontium is very close to calcium in the periodical table of the elements, and due to the chemical similarities between calcium and strontium, this ion can replace calcium in the structure of hydroxyapatite. And several studies have described that strontium compounds are able to decrease osteoclastic differentiation while sustaining osteoblastic mineralization ability. And that's a very important point, because the other hormonal-based therapies for treating osteoporosis are focused on decreasing osteoblastic differentiation and resorption activity, but these treatments are not able to increase mineralization by osteoblasts. So the focus of our study is getting advantages from the control of osteoblasts, but also trying to stimulate osteoblasts using strontium-based compounds. Strontium hanelate, that drug that I said to you 2 slides before, is this molecule. So we have 2 strontium ions per ranelic acid structure. Some adverse effects of strontium ranelate is also related to the high doses of ranelic acid in the human body. So our first try was to substitute this molecule using flavonoids. Flavonoids are natural compounds. They are very known and very studied due to these antioxidative properties. This is the general structure of a flavonol. And here we bound the strontium to the carboxylic group of morin, a highly hydrated flavonol. And we showed that this compound was able to support osteoblast mineralization and decrease osteoblast differentiation. So we reported the results of the preparation of this complex and also tested in vitro this ability of controlling osteoblast and osteoclastic activity. Oh, we first show that the compound strontium and strontium morin and only morin were safe to be used in osteoblast in vitro. We compared this also with strontium ranelate, SRR, here is the strontium ranelate. We tested the alkaline phosphatase activity in the presence of these compounds, and very interesting, we found that the mineralization, the alkaline phosphatase activity was enhanced in the presence of morin and morin strontium complex. We quantified the mineralization nodules, and we found that more mineralization was found using the strontium morin complex. So we tried to investigate why, what's this, maybe the signaling pathway that was being activated by this strontium morin, and we found that the expression of alkaline phosphatase related gene was increased in the presence of the complex strontium morin. It was not increased in the presence of the strontium ranelate, the drug, nor in the presence of poor morin, the flavonoid. But the fact of having strontium was very important for the gene expression that maybe resulted in also the increase of the activity of the enzyme. Alkaline phosphatase is the main phosphatase related to the control of inorganic and organic phosphate that will induce mineralization, important for inducing mineralization in vivo. So we also cultivated osteoclasts in the presence of this complex, strontium murin, and we found a decrease in the amount of osteoclasts being differentiated in the presence of strontium murin, and even also only in the presence of the flavonol. And we got no significant results in the presence of strontium ranelate. So no, it seems a little bit controversial since strontium ranelate was used as a drug. The point is to get some important reduction in the osteoclast differentiation in the presence of strontium ranelate, we need very high doses or very high amount of strontium ranelate. And that's the reason why the therapies with strontium ranelate lead also to pathological mineralization. So here we show that this new compound can decrease osteoclast differentiation, and it can increase osteoblast mineralization. And going further with the studies related to the synthesis of strontium-containing compounds for treating bone disease, we prepared some nanotubes containing strontium substituted calcium phosphate, inspired or bio-inspired in the building blocks of bone regeneration. Professor Barralet said that we got the best thesis in chemistry award in Brazil, and it was the work that was awarded, the study that was awarded here in Brazil. So what we did, what is special we did in this work? Before I say this to you, I need just to remind you that the nanometric structure of the bone is composed by mineralized collagen fibrils. And if we go to atomic scale, we will find some fibrils of collagen in which apatite can be mineralized at the surface or even inside the fibrils. So, another important thing, the D gaps in the collagen fibrous structure works as a confined medium in which the apatite crystals can nucleate and grow. So, but in the beginning, we try to investigate the effect of this physical confinement, trying to mimic the structure of collagen using these track-etched membranes. What we did was we immersed the membrane inside a solution containing the precursor ions, so phosphate, calcium, and strontium, with different percentages of strontium. So we exposed this system to ammonium vapor and carbonate generated by the decomposition of ammonium carbonate. And so with increase in the pH, the apatite minerals were precipitated inside these tubules of the track-etched membrane. Here I compare, just to prove you the effect of having the confinement, the structure of the particles precipitated in the absence of the membrane in the beaker, and the structure is precipitated in the presence of the membrane and isolated from these membranes. We got very well-organized nanotubes. Here, these tubes are 200 nanometers in diameter. And We also show here to you that somehow these structures resembles the structure of mineralized collagen fibrils that we found in vivo. So we were able to mimic the structure of mineralized collagen fibrils, but in the absence of collagen, only using physical confinement as a precursor in our synthesis. Here I show you only the structures to prove that by TMDX that the strontium is well distributed in the structure as well, calcium and phosphate. So we have no phase segregation. We also studied the composition, the difference in the composition guided by the presence of the confinement, the physical confinement. And it was very interesting also because more than difference in the structure, so nanoparticles and nanotubes, we got also difference in the composition of the particles that were formed using these two methodologies. So here we show that the formation of strontium apatite or even an apatite structure were favored by the presence of these confined, physical confined tubules in a similar way that we observe in vivo. We also tested the bioactivity of these nanotubes. So we immersed them in a simulated body fluid. And as you can see, apatite, some needle-like particles related to apatite structure were precipitated only at the surface of the nanotubes, showing that the induction of mineralization is site-specific. And these particles were also able to release strontium. We have studied this up to 21 days, and the amount of strontium released by the particles were related to the amount of strontium that were able to include in the tubular structures. So we applied these nanoparticles, testing their cytotoxicity in vitro using an osteoblast cell line, and we saw that the particles were not cytotoxic. The particles were also able to sustain mineralization, as indicated using alizarin red methodology. The morphology of the osteoblasts cultivated in the presence of the particles were not changed. So we went to the osteoclasts, and the result was very interesting. We cultivated the osteoclasts in the presence of the particles and also in the presence of some discs coated by hydroxyapatite. These holes that you can see here in the control are related to the resorption of the hydroxyapatite or the resorption of the minerals by the osteoclasts. So we found the resorption, the control, in the absence of the nanoparticles, in the hydroxyapatite poor nanotubes, and we see that the resorption area was diminished in the presence of the nanotubes containing 50% of strontium and also 100% of strontium. With 100%, the resorption area was 0. The osteoclasts were not able to resorb the bond. So here we show that using lower dosage of strontium, milligrams per liter, we were able to deactivate the osteoclast. And so again, the relevance of low doses of strontium in osteoporosis treatment. In this other study that I'm quoting here, we investigated the effect of strontium in the quality of the mineral formation, and we found that a high amount of strontium disturbs the crystalline structure of apatite. So using high amounts of strontium is not good for the quality of the mineral that is formed in vitro. So just to close this story about the nanotubes, we were able to reproduce the building block of bone, that is collagen, collagen mineralized fibrils, using only the confinement and the inorganic part of the bone. And it can be, we know that the effect of nanotubular structures have been reported since the 90s, since last century. So these materials can be used also as a fillers for biopolymeric materials or for other polymeric materials to enhance the mechanical properties and also to deliver strontium, controlling also the activity of the bone-related cells, osteoblasts and osteoclasts, for instance. This methodology is quite versatile. We got also strontium containing, calcium carbonate containing strontium nanotubes. We used these nanotubes to change the surface of titanium by depositing the structure with collagen in a layer by layer-ish structure. And we also precipitated calcium carbonate using modifying the surface of the structures also with collagen. So the third material that I will show you is a material that gave us the patent about the organic coatings. And in this study, we prepared some organic and inorganic biomimetic coatings containing strontium. As organic portion, we used phospholipids negatively charged, in which we bound strontium and calcium to grow the minerals. These films were deposited on implants, and we implanted these materials in osteoporotic mice, obviously in collaboration with my colleagues from the dentistry school here in Brazil. They had these animals, these osteoporotic animals with lower bone density compared to the control. They induced osteoporosis using ovactomization. Sorry. So what was the idea here? Why I'm saying that we were using a biomimetic coating on titanium? If we think about the first contact of an implant with the bone tissue is between a surface, metallic surface composed by titanium oxide and a surface composed by cells, by proteins, by minerals. And so there is no chemical similarities between these two interfaces. Using our methodology, we were able to create a biomimetics of a cell membrane using these Langmuir monolayers. We tried to reproduce the composition and the organization of a cell membrane by adding phospholipids. And we can also add enzymes and proteins to these lipid monolayers. And so we deposited this on titanium or another surface of interest to study first the activity of the enzyme. Here we studied the activity of alkaline phosphatase, and we saw that we were able to induce mineralization, use this alkaline phosphatase immobilized on phospholipid membrane. We used also this membrane to coat titanium and to deposit the minerals. So This data has not been published yet. We are finishing the manuscript, but so I will report to you maybe the two most important results. We found that the force needed to remove the implants from the bone or from the femurs of the mice were higher using this G3 here, and G2 is the strontium containing coating. So the force needed to remove the implant from the bone after the implantation was higher compared to the control using only hydroxyapatite, and higher than the poor titanium surface, the uncoated titanium surface. We have also studied the new bone formation on these animals, and these figures are related to the health animal, and below on the osteoporotic animal. And we found in green, we see the new bone formation, and we found that the surface containing 10% of strontium were better to induce mineralization in the health animals. We found also an initial mineralization in the osteoporotic animals higher to the mineralization found in the control. So here we have two good results. First, the coating containing only 10% of strontium were better than poor hydroxyapatite surface, were better than the surface containing high amount, 90% of strontium, and it goes in the same way of the minerals that we produce in vitro, showing that low amount of strontium are better to induce mineral formation. And here, even using the osteoporotic animals, although the mineralization was not good as we found in the health animal, the mineralization was better using also the 10% of strontium. The point is, maybe we need more time of implantation in the osteoporotic animals. And so the last also unpublished data that I show you is some bone cements that we have prepared also in the presence of strontium. We used PMMA, that is a polymer very used for bone replacement surgeries. We tried to induce or to enhance the bioactivity of the cement by adding hydroxyapatite, and hydroxyapatite contains strontium. This problem came from a colleague from the medical school. He came to my lab and he said that the patients that he implanted with PMMA after 10 years were suffering from detachment of the implants. So he wants a new material containing some bioactive compound that could enhance the mineralization and the fixation of the cements in vivo. So I suggested him to use these particles that I have prepared. Also thinking in control first the release of strontium and controlling so the activity of osteoblasts and osteoclasts like in the other materials that I have prepared. So first I prepared some nanoparticles, hydroxyapatite nanoparticles containing strontium, and I compared the structure of these particles with the structure of the bone by XRD, and we can see that the peaks, the Bragg reflections of the bone and the Bragg reflections of the particles were quite similar, so we were able to produce a structure close to the one found in bone. Also, using the infrared spectroscopy that related more to the composition, not to the crystalline structure, we also found similarities between in black, the hydroxyapatite nanoparticles that we have prepared, and the composition of the bone tissue. So we added these nanoparticles to the bone cement, the PMMA bone cements that we have prepared, This microtomography image here, you can see this whiter dot that's related to the presence of the particles. We also induced this pore formation using bicarbonate to try to get some interconnected pores for cells penetration and to enhance vascularization. And we studied the release of the strontium compounds by the cements, and we were able to deliver strontium in vitro in a wide range of concentrations by tuning the amount of strontium in the hydroxyapatite nanoparticles structure. So this can be a sort of personalized medical application of these nanoparticles, since we can choose exactly the amount needed for each patient to recover the bone. That's only my chemistry dream, you know. Okay, so we studied the effect of these bone cements in the osteoblast mineralization. We showed that the cells were able to penetrate the cements, as we can see here by the side view of the cements cutted after incubation with the osteoblasts. We found also enhanced mineralization. This purplish or reddish color we can see here compared to the control is related to the control in absence of cells. It's related to the formation of minerals. And here we quantified the formation of minerals, and we're also able to investigate the morphology of the cells in the presence of the bone cement, the osteoblast cells in the presence of the bone cement. So here we got a material that, compared to the control in the presence of the strontium, also enhanced mineralization. With this kind of materials, now we are going to investigate the effect on osteoclasts and also the in vivo effect using rabbits. And so, as a final remark of my talking, I hope I showed to you that strontium can promote mineralization by activating the expression of alkaline phosphatase gene and also enhancing the activity of this enzyme. The strontium compound is versatile due to its similarity with calcium, but we have to pay attention because some pathological mineralization and under high doses of strontium can occur. So we must investigate this carefully to guarantee the safety of the treatment. And obviously, here I'm talking about the local delivery of strontium that is different when a patient is injecting strontium granulate. So if we treat locally bone defects, these materials can be safe, but we have not investigated the uptake of these materials in vivo. So it's our limitation for now. So I'd like to thank my collaborators, my main collaborators, and my students, Larissa, Marcus, Camila, and Fernanda, that were the winners of the 4 studies that I have presented to you. I thank the rest of my group and the Brazilian funding agents for supporting this research. And thank you very much for your kind attention.
That was great. Thank you very much. Does anyone, Paxton, you'll have to help me monitor questions. So I think someone has a question. There's a comment. Okay. If anyone has any questions, please put them in the chat, and I'll try and keep an eye on them.
Can I stop sharing, or I leave the screen?
Maybe, I don't know, if you need the slides to discuss anything, then you can leave them. It's okay. I know what the students look like. So, yeah, I think some of the images you showed us were striking. I particularly was very impressed with your resorption pits on your. Excellent. I mean, I've worked on that with Professor Komarova, so I know how difficult that is to achieve. I was wondering if you could just I'm following the strontium activates ALP expression, but how does strontium stop osteoclastic resorption?
Yeah, that's an interesting question. We are now investigating some genes related to osteoclast. I don't have an answer to give to you right now, but it seems that strontium also regulates the expression of some osteoclast related gene.
Right.
And yeah, it's some pathway this way.
That's pretty interesting. And the first study, then you were showing, was it strontium complexed with, was it Morin?
Morin, yeah, Morin.
Yeah. And the idea was that Morin is like an antioxidant. So could you explain a little bit more about, I mean, that showed really great results. Do you think if someone took strontium Morin orally, that it would could be a safer systemic delivery, or were you thinking it should be local delivery?
No, yeah, the idea is using the Morin to deliver strontium, and the flavonols are safe. I don't know. No, so we have flavonols anywhere, in fruits, in juices, everything we uptake. So, but I don't about the strontium, and when it's complexed with a cation, I don't know about the safety. That's, in my opinion, that the lack of our studies. So we have here, I'm a chemist, I have no way, I have to look for collaboration if I want to test this in vivo or in biological systems. And so, yeah.
Well, I think in general, it's interesting because with a lot of inorganic, bioactive inorganic compounds, there's not much attention paid to what they are associated with.
Yeah, and people use these flavonols for everything, so it's a way like to sell a substitute for strontium ranelate, saying that somehow the flavonols per se are safe. So, but I'm not sure, I'm only saying about everybody says what everybody says, but we have never tested.
Yeah. And because going back to your osteoclast, anti-osteoclast strategy, or your demonstration of this anti-osteoclastic effect, bisphosphonates were originally thought of as something that would reduce mineral solubility. And the effect was thought to be very simple, but in the end, it turned out to be pretty complex, and it took quite a long time to understand it. And now, bisphosphonates are used a lot in trying to prevent not only osteoporosis, but resorption of the skeleton by tumors and so on. So very interesting. And in your templating, when you had your membrane with the channels, why was that different? Why was everything different inside the channels? So why were you getting a different phase?
Because we changed the supersaturation conditions of the system. So we control the nucleation and the growth of the crystals of the minerals better than in bulk solution.
Right.
So yeah, and it's an effect of supersaturation.
Okay. And
it's similar what happens in vivo with that kind of sea animals, the orkin structures.
right.
You know, in shells, in seashells. So we control the precipitation of aragonite, calcium carbonate. It's not the most thermodynamically stable, because calcite is the most thermodynamically stable, you know, just controlling the pores structure.
Mm. I thought it was interesting that the mineralization was kind of, was not everywhere, it was just inside the...
we restricted the supersaturation to these confined spaces.
Right, right. Okay, does anyone else have any questions?
Yeah, so that's a very interesting presentation. And congratulations, so Odin, nice award. Do you think that strontium is also angiogenic? Because you are showing its effect on osteoblasts, good effect on osteoblasts, and you are also showing that in terms of osteoclast, you get a reduced activity. So do you think it's also pro-angiogenic?
I don't know. I don't have the answer. I have studied strontium only with the osteoblasts and osteoclasts, but you know, since I got some positive results with just two cells, I hope I can get some interesting results, you know, about angiogenesis. Maybe you can help me in testing this. No, I don't know if people have tested this. But I look more for the mineral formation, the mineral parts. So because of this, I'm more interested in the bone-related cells. We tested them also using chondrocytes, and we got positive results. No, in the very beginning of the study. So because of this, I didn't show you. But we isolated chondrocytes from chicken embryos, and we grow the chondrocytes, and they mineralized more also in the presence of these strontium compounds.
Okay, so one thing that you alluded to, because as you were giving the presentation, I was thinking in terms of having this like a 3D printed osteoinductive construct that's releasing strontium, and then so that it can do all the nice things, improving osteogenic differentiation, etc. But then you brought in a caveat, which is that you have to be careful how much strontium is released. So in vivo, how would you control that in vivo?
We can control the release by changing the structure of the pores of the scaffold. We can control the concentration. We can control the concentration of the particles, the concentration of strontium inside the particles. That's the point. No, I'm not only adding strontium, but I'm showing that the materials that we prepare can accommodate strontium with different amounts. So I can control the amount of particles that I add to the material. I can control the amount of strontium that I add to the particles before adding the particles to the scaffold. So, you know, we have a very tiny control of the concentration range using these parameters. But in vivo, in my opinion, maybe the most important is the presence of the pores and how the strontium will be released. You know, so, but for now we have no data. We are testing. A collaborator my collaborator in the medical school is testing in rabbits, but I don't have the results for now.
Okay, so my last question is or comment is when you are talking about strontium's effect on decreasing osteoclast formation or activity. So I was thinking that it may be interfering with the NF-kappa B pathway or the activator of NF-kappa B pathway, because that's where you would be getting this kind of effects where you are interfering with the osteoclast formation, differentiation, or activity. Is probably what is anyone looked at that pathway?
Yeah, we have tested different tons of osteoclast pathways, and it's one of them. But we are also in the beginning of the studies, and I'm studying the osteoclasts, the signaling with a colleague from the pharmacy school. And yeah, I hope in the near future I have an answer to give to you.
Okay, thank you very much.
Thank you for your suggestion.
Thank you.
Any shy students feeling less shy? Does that make people feel less shy, or
do you have Brazilians around? Because I saw some names, and maybe
we have quite a few Brazilians.
Yeah, I saw Daniela Vieira. It sounds like Brazilian.
Yeah. Do all the Brazilians want to say hi? They're very shy.
Hi.
Hello, Daniela. Nice to meet you.
Nice to meet you.
So we're going to switch to Portuguese now. So yeah, just last thing, you're saying that sodium renylate drug was taken off the market because it induced vascular calcification. I thought that was pretty interesting, because that wouldn't happen through ALP activation, right? So do you have any information or knowledge about vascular calcification caused by strontium?
Yeah, that's what I was saying to you. I would like to test the effect of this compound now in vascular calcification to see if the effect was related to the high amount of strontium in the strontium ranelate, or if it were related to the presence of the renalic acid, the ligand. Because it can also be toxic, and the renalic acid can also induce some response. So I'm not sure if the effect is really about the strontium, maybe the bioavailability of the strontium and how it's bound to renalic acid. I'd like to test these compounds now using vascular smooth muscle cells, maybe cultivate vascular smooth muscle cells and see if they differentiate into a blast phenotype. No, it can be a pathway related to these vascular diseases that people found using strontium ranelate. There are some things to be investigated in this way. We don't know if it's some inflammatory pathway that can also induce mineralization, but it's a way that I would like to investigate, going for the pathological mineralization view more than the physiological.
Brilliant. Thank you very much. So last thing, maybe this will wake up our trainees. How difficult would it be for a trainee to come and do a short visit in São Paulo University with you?
In Brazil, we have lots of fellowships to foreign students for training. So if you are interested in being in here for a couple of months or for 1 year, we can try to apply to FAPESP to have some visiting. FAPESP is more related to São Paulo State, but we have the caps for the national, for the federal government, the CNPq from the national government. So we have a way to get funded. Also having funding from Brazil to receive students. I have 2 big grants now that is carrying on. One about the 3D printing, and we are printing structures with strontium, and it will be very nice if you have some person with some biological skills to to be here to help us with this. And we have also the other project with the Johnson nanoparticles, not the scaffold, that it's in the last year. So we can also have students here. And I have to say to you that Ribeirão Preto is a very pleasant city. It's not huge as São Paulo city, but it's a huge city in São Paulo state, maybe the third in São Paulo state. And we have, everything that São Paulo city has, but, it more personalized, more soft things, not traffic, like we have in São Paulo, not a rush as we have in São Paulo city. So it's a very pleasant place to live. I don't know if Daniela knows Ribeirão, if she's from São Paulo state, but it's a very pleasant place to live.
Well, that sounds fantastic opportunity. So if any students can match their skills to that project, then that would be a great opportunity, especially as January and February arrive, because that would be your peak summer, right? So I'd like to thank you. Go on, sorry.
No.
I'd like to thank you very much for taking the time to show us your work. And apparently you have the best beer.
Yeah, I forgot to say this. Yeah, Julio is right. We have the best beer in Brazil. So we have a good university, good people, good city, and the best beer in Brazil.
I think you're going to be overwhelmed with, mass exodus.
It's amazing. It's a very nice place.
Okay, so Professor Ramos, thanks a lot.
Someone asked if Portuguese is required. Someone asked in the chat. No, at the university, you will find people speaking English, everywhere. So everybody at the university speaks English. But maybe in the city, it will be more difficult. But with some basic words, we can live well in Brazil. Brazilians are very friendly. If you try, to make them to understand you, use your hand, use your head. They will stop and pay attention to you to try to understand what you are saying if you don't know how to speak Portuguese. So no, I think that the friendly in Brazil is the mark of this country.
Fantastic. Brilliant. So thank you once again. And it's very, very interesting. I'll look forward to discussing this with you in more detail. Thanks everyone for coming. Thanks Oliver for a great talk as well. And have a great afternoon.
Thank you very much again, and bye-bye. Hope see you soon.
Yeah, take care.